Okay, let's try and unpack this. April 28th, 2025, big blackout. Spain, Portugal,
Yeah, huge event, millions of people affected, right across the Iberian Peninsula.
and not just a flicker. We're talking, what, up to 18 hours in some places? Everything just stopped. Transport, phones.
Pretty much ground to a halt. Public services struggled. It was definitely one of the worst they've seen.
And predictably, the internet did its thing. Theory is everywhere, like instantly.
Oh, yeah. That always happens when something big goes down, especially the power grid. People need answers, or at least theories.
And you had the usual suspects, politically motivated stuff, pointing fingers at renewables.
That came up.
But the one that really seemed to catch on, the big one, was maybe a solar storm was the culprit. People were genuinely asking, did the sun do this?
Well, it's not a totally crazy thought on the surface. I mean, the sun does affect Earth, sometimes dramatically. Space weather is a real thing.
Right. So that's kind of our job today in this deep dive. We're not here to solve the blackout mystery. Sounds like that investigation is still chugging along.
Exactly. No definitive cause announced yet.
But what we can do is dig into solar storms themselves. Like, what actually are they? How do they mess with things down here on Earth? And, could one realistically have caused that massive outage? We need some clarity.
Let's do it. Moving beyond the social media speculation. So solar storms, fundamentally, they're these enormous releases of energy from the sun.
Like the sun throwing a massive tantrum.
Yeah, you could say that. It involves energy, magnetic fields, actual solar material getting blasted out into space.
And it's all tied up with the sun's magnetic field, which sounds incredibly complicated, like tangled and messy.
It is very complex, very dynamic. Think of magnetic field lines on the sun getting twisted up, stretched, and eventually they can snap and reconnect somewhere else. It's a process called magnetic reconnection.
Like rubber bands snapping.
Exactly.
Yeah.
And that snap releases a tremendous amount of energy. That's the engine behind these solar events.
Okay, so it's not just one type of solar storm. It's like a whole menu of potential problems. Let's start with solar flares. Those sound quick.
They are. Solar flares are sudden, intense bursts of electromagnetic radiation. Basically light, but across the whole spectrum. Radio waves, X-rays, even gamma rays.
Oh, wow. Like a flashbulb going off, but like way more intense and covering everything.
Pretty much. And because it's radiation, it travels at the speed of light. So it hits Earth in about 8 minutes.
8 minutes. That's incredibly fast. No warning, really.
Nope. Real-time impact.
And they have grades, like earthquakes or hurricanes. A, B, C, M, X. X is the big one.
That's right. X-class flares are the most powerful. It's a logarithmic scale, so each letter jump is 10 times stronger. And yeah, there's no theoretical upper limit, but the record is something like an X28.
X28, okay. And what do these flares actually do to us?
The main effect is on radio communications, specifically high-frequency radio on the side of the Earth facing the sun at that moment. The X-rays ionize the upper atmosphere, and that absorbs the radio waves. So you get radio blackouts.
So pilots flying over the ocean, for example, might suddenly lose contact.
Exactly, particularly over the sunlit side.
Okay, flares. Fast radiation, mess with radios. Got it. What's next? Coronal mass ejections? CMEs. These sound more substantial.
They are. CMEs are enormous clouds of plasma that superheat in gas, charged particles, and magnetic fields that get expelled from the sun's outer atmosphere, the corona.
So not just light, but actual stuff being thrown at us.
Actual stuff, yes. Billions, tons of it sometimes, traveling at millions of miles per hour.
Millions. Still slower than light speed, though.
Oh, definitely slower. They typically take 1 to 3 days to reach Earth.
Okay, so there's a bit more warning time with these.
Yes, potentially. If we see one leave the sun and it looks like it's headed our way, we have some lead time, maybe as little as 18 hours for a really fast one, but usually longer.
And these are the things that cause the geomagnetic storms, the ones that mess with the power grid.
That's right. When a CME slams into Earth's magnetic field, our magnetosphere, it can trigger these disturbances. It compresses the field, transfers energy. It's a major event for our planet's magnetic environment.
Right. Our planetary force field gets rattled.
Yeah.
Okay, flares, CMEs, you mentioned a third type, SCPs.
That's CPs, yeah. Solar energetic particle events.
Yeah.
Sometimes called solar radiation storms.
More radiation.
Well, particles this time, mostly protons, accelerated to really high energies during these solar eruptions, flares or CMEs.
And are they fast?
Very fast. Almost the speed of light sometimes. They can arrive here in maybe tens of minutes to a couple hours after the eruption.
So faster than CMEs, but slower than the flare's light.
Generally, yes. And these are a concern for different reasons.
Like what?
Primarily radiation exposure risk for astronauts, especially if they're doing a spacewalk, and also for passengers and crew on high-altitude flights, particularly those flying over the polar regions.
Ah, because the poles are where Earth's magnetic shield is weaker.
Exactly. They also can interfere with satellite electronics and, again, polar radio communications.
Okay. And then there's just the regular solar wind. That sounds pretty harmless.
It's the constant outflow of particles from the sun. Usually it's relatively gentle, but it can vary. Sometimes you get these high-speed streams coming from areas on the sun called coronal holes.
Coronal holes. Sounds ominous.
They're just cooler, less dense regions where the sun's magnetic field lines extend outward into space instead of looping back. These streams can buffet Earth's magnetosphere, too, causing milder geomagnetic disturbances, like a persistent gusty wind rather than a huge storm.
Gotcha. So it's a whole bunch of related but different things happening on the sun, each with its own way of impacting Earth. Flares, CMEs, SAPs, even variations in the solar wind. It's complicated.
It really is. Understanding how an event on the sun translates into an effect at Earth involves a lot of physics, a whole chain of events. It's not always straightforward.
Okay, super helpful overview of the cosmic fireworks. Now let's bring it back down to Earth, specifically that Iberian blackout in April 2025.
Right.
Huge outage, Spain, Portugal, bit of France, lasted up to 18 hours. Massive disruption. Spain's grid lost, what, 15 gigawatts?
Reportedly, yes. A huge drop, about 60% of their demand at the time. I mean, that's a catastrophic failure in grid terms.
Just vanished. So naturally people think solar storm. But what's the official word now that some time has passed? Is the investigation pointing that way?
Well, as of early May 2025, the official investigation is ongoing. No single cause has been formally declared.
Okay.
But crucially, the grid operators themselves, Red Electrica in Spain, RN in Portugal, they've been pretty clear in downplaying or even denying that space weather or any atmospheric phenomena were the cause.
Really? So the people running the grid are saying, nope, wasn't the sun.
That seems to be the message coming from them, yes.
Huh. So if it wasn't a solar storm, what are they looking at? Just things breaking?
The focus seems to be on internal technical faults within the power system. There's talk of a possible sequence of failures starting somewhere in southwestern Spain, Extremadura maybe. Yeah. They mentioned things like grid frequency instability, sudden big swings in power flowing between countries, and apparently a sharp drop in solar power generation around the same time. But untangling how all those pieces fit together takes time. It's complex system forensics.
Right. It's never just one thing flips a switch. It's usually a cascade.
No.
So the solar storm theory, while popular online, isn't supported by the operators.
Not based on their public statements, no.
But that didn't stop the speculation, did it? I saw talk of cyber attacks, even some old fire in France being blamed.
Oh, absolutely.
Yeah.
Big failures like this always create an information vacuum, and speculation rushes in. The solar storm idea was prominent, but yes, cyber attacks were mentioned, initially ruled out, but apparently being looked at again by courts. And that old fire story resurfaced too. It's typical noise around a major incident.
And even some major news outlets were mentioning solar energy issues, even if they weren't sure of the trigger.
Yeah, the Wall Street Journal piece pointed toward solar energy, though the exact trigger wasn't clear. But then you had the EU Energy Commissioner warning against jumping to simplistic conclusions, like just blaming renewables.
Especially since some renewables apparently kept working through it.
That's been reported, yes.
Yeah.
Which makes a simple renewables failed narrative less likely, especially if linked to a supposed solar event.
Okay, so bottom line on the Iberian blackout. Currently, no credible evidence points to a solar storm. The official investigation is leaning towards technical grid failures. The space weather link seems unlikely based on what the operators are saying.
That appears to be the most accurate assessment based on available information right now.
Right. So let's pivot back to what solar storms can actually do, because they can cause major problems even if they didn't cause this particular blackout. Let's talk Earth impacts. Geomagnetic storms first. That's the CMEs hitting our magnetic shield.
Exactly. Earth's magnetosphere does a great job protecting us most of the time. But a powerful CME impact can really shake it up.
How does that work?
It transfers energy into the magnetosphere. And a key factor is the magnetic field within the CME cloud, the Interplanetary Magnetic Field, or IMF. If that field points southward, opposite to Earth's northward pointing field at the equator, then energy transfer is much, much more efficient. It opens a door, essentially, for solar wind energy to pour into our system.
Like magnets snapping together instead of repelling?
That's a decent analogy, yeah.
Yeah.
And that energy surge drives the geomagnetic storm.
And we measure these storms. There's a scale.
Yes, the NOAA G scale. G1 is minor, G5 is extreme.
Okay, so what happens at different levels? G1, G2, not much. Maybe some nice aurora up north?
Pretty much weak grid fluctuations possible, minor impacts on satellites, aurora visible at high latitudes. Things get more serious at G3.
How serious?
You might need voltage corrections on the power grid, maybe some false alarms on safety devices. Satellites can experience surface charging, increased drag for low-orbit ones, and you can get intermittent problems with satellite navigation and low-frequency radio.
Okay, getting dicey. G4.
Now you're looking at potential widespread voltage control problems. Protective systems might trip transformers or lines at a service, potentially causing blackouts, more significant satellite issues, navigation problems, and the aurora moves down to lower latitudes, maybe visible in the northern U.S. or mid-Europe.
And G5, the big one.
G5 is extreme, severe impacts. Widespread voltage control problems are likely, potentially grid collapse, widespread blackouts. Transformers could be permanently damaged. Major satellite problems, high-frequency radio blackouts lasting days, and aurora visible maybe down to Florida or Texas.
Wow. Aurora in Florida sounds cool, but grid collapse, not so much. You mentioned transformer damage. How does that happen, these GICs?
Geomagnetically induced currents, yeah. During a storm, the Earth's magnetic field is fluctuating rapidly. That induces electrical currents in long conductors on the ground.
Like power lines.
Exactly. Power lines, pipelines too. These GICs flow into the high-voltage transformers at substations.
And transformers don't like that.
Not at all. They're designed for AC current. GICs are quasi-DC, very low frequency. They can saturate the transformer's magnetic core.
Saturate, like overload it.
In a way, yes. It causes the transformer to operate inefficiently, generate harmonics, basically electrical noise overheat, and potentially suffers physical damage. It can also cause voltage instability across the whole grid,
Which leads to...
protective relays tripping, equipment damage, and potentially large-scale blackouts.
And this isn't theoretical, right? Quebec, 1989.
The classic example, a G4, G5 level storm hit. The Hydro-Quebec grid collapsed in about 90 seconds. 6 million people lost power for 9 hours, all triggered by GICs.
90 seconds?
Yeah.
That's terrifyingly fast, a huge wake-up call.
Absolutely. It really highlighted the vulnerability of modern power grids.
Okay, so power grids are definitely at risk. What about satellites? You mentioned surface charging and drag.
Right. The high-energy particles, especially during SB events or strong geomagnetic storms, can build up charge on satellite surfaces or penetrate inside, damaging sensitive electronics or solar panels.
And the drag.
During a geomagnetic storm, Earth's upper atmosphere heats up and expands. For satellites in low Earth orbit, like Starlink and many others, this means flying through denser air.
Like hitting atmospheric speed bumps.
Sort of, yeah. It increases drag, which causes their orbits to decay faster. They need to use more fuel for station keeping, or their lifespan is reduced. It's a growing problem with these huge constellations.
Makes sense. And GPS, our beloved navigation system, can solar storms mess with that too?
Yes, significantly. Geomagnetic storms and solar flares disrupt the ionosphere, that layer of charged particles high above us that GPS signals travel through.
How does the disruption affect the signals?
It can cause fluctuations in the signal path, delaying the signals or making them scintillate, kind of like twinkling starlight. This degrades the accuracy of GPS positioning, sometimes significantly, or can even cause loss of lock altogether.
And we use GPS for everything. Planes, ships, farming, construction.
Even financial transactions rely on precise timing from GPS, so ionospheric disturbances can have really widespread impacts.
Okay, so grid problems, satellite problems, navigation problems. What about radio blackouts again? That was the flares, right?
Flares are the primary cause, yes.
Here.
The X-rays hit the D layer of the ionosphere on the sunlit side.
Making it absorb radio waves.
Exactly. High frequency, or HF radio, which is used for long-distance communication over the horizon radar, ham radio, aviation, maritime comms, gets absorbed instead of reflecting off the ionosphere.
And there's a scale for this, too.
The NOAA R scale,
Cop.
R1 to R5. R1 is minor, R5 is an extreme blackout, potentially lasting hours, affecting all HF communication on the entire sunlit side of Earth.
That sounds like a big deal for planes flying polar routes where satellite communication might be patchy.
It is. They rely heavily on HF radio, so an R3, R4, or R5 event can be a serious issue for communication. Add in potential GPS errors and increased radiation exposure, and you see why aviation takes space weather seriously.
Right. Okay, so lots of potential technological chaos, but there is a beautiful side effect, right? The aurora.
Absolutely. The northern and southern lights. They're caused by those charged particles from the solar wind and CMEs hitting gases high in our atmosphere.
Making them glow.
Precisely. The particles excite the oxygen and nitrogen atoms, and when those atoms relax back down, they emit light green, red, blue, violet.
And the stronger the storm, the further south or north you can see them.
Exactly. A G5 storm can push the main auroral oval way down, making aurora potentially visible in places that almost never see it, like the southern U.S. or southern Europe.
Amazing. So we've talked about the potential. Have there been any really monster storms historically? You mentioned Quebec. The big one everyone talks about is Carrington, right?
The Carrington event of 1859, still the benchmark. It was an absolutely massive storm.
What happened?
Telegraph systems worldwide went haywire. Operators reported sparks flying from equipment. Some even got electrical shocks. Papers reportedly caught fire from the sparks.
Seriously, fires.
That's the report. And the aurora was seen globally, incredibly bright, even down in the tropics, Cuba, Jamaica, Hawaii. People thought it was dawn in the middle of the night.
If something like that hit us today with our reliance on electricity and electronics.
The estimates run into the trillions of dollars in damage. Widespread, long-lasting blackouts, potentially cascading failures across multiple infrastructures. It would be catastrophic, truly society-altering.
Trillions. Wow. And we had a taste of a big one more recently, didn't we? May 2024.
Yes, that was the strongest geomagnetic storm since 2003, a G5 event. It produced spectacular aurora seen all over the world. NOAA issued its first G5 warning in nearly 20 years. It was caused by a series of flares and CMEs from a very active sunspot region.
So a reminder that these things still happen.
Definitely. And there's evidence in tree rings, from analyzing carbon-14 levels, of even stronger events in the prehistoric past, these Mayak events, possibly much stronger than Carrington.
Mayak events, never heard of those. Stronger than Carrington.
Potentially, yeah. Based on the huge spikes in radioactive carbon isotopes found in tree rings dated to specific years, like 774, 775 AD. They suggest incredibly intense bursts of solar energetic particles hit Earth.
Okay, so the sun is capable of some truly epic tantrums. Extreme events are rare, but the potential impact on our modern tech-dependent world is huge. Everything's connected.
That interconnectedness is key. A failure in the power grid affects communications, which affects transport, which affects supply chains. It's a domino effect. Our vulnerability has definitely increased.
Right. Let's talk about health. We ground dwellers are mostly safe from direct radiation, you said. Atmosphere and magnetic field protect us.
Largely, yes. For people on the surface, the direct radiation dose from even a major solar storm is negligible compared to other sources like medical X-rays or even just background radiation over time. But the atmosphere is a fantastic shield. Much more risk from regular UV exposure over your lifetime.
Good to know. No need for tinfoil hats just yet, but astronauts, people on planes.
Different story. Astronauts, especially outside the spacecraft on an EVA, face significant risk during a major solar radiation storm, an S4 or S5 on the NOAA scale. There's risk of acute radiation sickness, increased cancer risk later. NASA has shelters on the ISS and strict procedures.
And airline passengers.
Passengers and crew on high-altitude flights, especially polar routes, do receive an increased dose during solar radiation storms, S2 or higher. It's usually comparable to a chest X-ray or so. Not acutely dangerous, but airlines monitor space weather and might reroute or fly at lower altitudes to minimize exposure.
Okay, so direct risks are manageable or limited to specific groups. But the indirect health impacts, those sound like the bigger worry for the general public.
Absolutely. If the power goes out for an extended period due to a storm.
Yeah.
Think about people relying on home medical equipment like oxygen or dialysis, loss of heating in winter, cooling in summer, food spoilage, lack of safe drinking water if pumps fail, communications down so you can't call for help easily.
Hospitals would struggle too, even with backups.
Backups have limited fuel. A really prolonged outage could overwhelm healthcare systems. Transportation paralyzed, so emergency services can't get through, supplies run low, and the psychological stress, potential for social unrest. The indirect consequences are the main threat to public health and safety.
That's a really important distinction. It's not the space radiation itself, it's the failure of the systems we depend on.
Precisely. And that needs to be clear in how we prepare and communicate about these risks.
Okay, so given these potential impacts, what are we doing to watch the sun and predict these events? Space weather forecasting is a thing now, right?
It is. There are dedicated agencies like NOAA's Space Weather Prediction Center, SWPC, in the U.S., and international collaboration through organizations like ICES. They monitor the sun 24/7.
Using what? Special telescopes? Satellites?
Both. We have satellites like the GOES series constantly watching the sun for flares and imaging CMEs. Critically, we have satellites like DSCO-VR positioned between Earth and the sun at the L1 point.
L1? What's that?
It's a gravitationally stable point, about 1 million miles towards the sun. DSCO-VR sits there and measures the solar wind speed, density, magnetic field before it reaches Earth.
Giving us a heads up.
Exactly. It provides about 15 to 60 minutes warning of incoming geomagnetic disturbances. There's a new satellite, SWFO-L1, planned to enhance this capability soon. Plus, missions like SOO provide detailed images, and Parker Solar Probe is actually flying through the sun's outer atmosphere. And lots of ground-based telescopes and magnetic observatories contribute too.
So we have eyes on the sun, but prediction is still hard. Predicting exactly when a flare or CME will happen and if it'll hit us.
It's still very challenging. We can see active regions, track sunspots, but predicting the exact timing and intensity of an eruption is tough. Predicting if a CME will actually impact Earth and how strong the impact will be is also complex. CME warnings are typically hours to days. Flare warnings are essentially zero. We detect them as they happen because the radiation arrives so fast.
Right. So forecasting helps, gives some warning, but it's not perfect. Which means we also need to protect our infrastructure. How do we do that? Harden the grid?
That's a major part of it, making the grid more resilient. This includes things like upgrading equipment, implementing operational procedures like reducing power flows on vulnerable lines during a storm warning, and installing devices to block or mitigate those GICs.
Like what kind of devices?
Things like series capacitors or neutral grounding resistors that can limit the flow of GICs into transformers. Designing smarter, more segmented grids, self-healing grids, can also limit the scale of outages. Putting power lines underground helps too, though it's expensive.
Makes sense. What about satellites? Can we shield them?
To some extent, shielding critical components helps. Using radiation-hardened electronics is standard practice for many missions. Operators can also put satellites into a protective safe mode during expected storms, turning off sensitive instruments, and adjusting orbits slightly to manage drag.
And our communication networks, data centers.
Similar principles. Physical shielding, like Faraday cages, can help against electromagnetic pulses. Surge protectors, robust grounding, shielding key components, and crucially, having reliable data backups, probably off-site and maybe even air-gapped, totally disconnected from the network. EMP-resistant communication methods are also being explored.
And aviation just reroutes flights.
Based on forecasts, yes. Adjusting routes, especially polar ones, and altitudes is common practice during space weather events.
Even finance is looking at backup timing systems because GPS might go wonky.
Exactly. Having land-based atomic clocks or other timing references that aren't reliant on potentially disrupted satellite signals is becoming more important for critical timing applications.
It sounds like a huge effort across many sectors. Needs lots of collaboration.
It absolutely does.
Yeah.
Science, engineering, operations, policy, plus international cooperation for monitoring and data sharing. It's not cheap or easy, but it's increasingly necessary.
So that's the big picture. What about us, regular folks? What can we do to be prepared, besides not panicking?
Individual and community preparedness is really important. It complements the larger efforts.
So like having an emergency kit.
Definitely. The basics you'd want for any extended outage. Water, non-perishable food for several days, flashlight, batteries, first aid supplies, any essential medications. A battery-powered or hand-crank radio is vital for getting information if the internet and cell service are down.
And a plan, like how to contact family if phones don't work.
Yes. Have an out-of-state contact everyone can check in with. Know where you'd meet if you got separated. Have backup power for your phone or other critical devices if possible.
What about during an actual event, like a long blackout?
First, stay calm and get information from official sources. That radio will be key. Verify information, don't spread rumors, conserve power on your devices. If officials say to unplug sensitive electronics to avoid damage from surges when power comes back, check on vulnerable neighbors.
Practical stuff too, like keeping the car fueled.
Good idea. Keep it at least half full. Gas station pumps need electricity. Know how to open your garage door manually. Be mindful of food safety in your fridge and freezer. Have a plan for medications needing refrigeration.
It sounds a lot like preparing for a hurricane or earthquake. Same basic principles.
Very similar. It's about resilience and self-sufficiency for a period of time and looking out for your community.
Okay, looking ahead now. We know the sun has this cycle about 11 years, right? Solar minimum, solar maximum.
Approximately 11 years, yes. It varies a bit.
And we're in cycle 25 now. Where are we in that cycle? Are we near the peak?
Cycle 25 started in December 2019. The initial predictions suggested a relatively weak cycle peaking around mid-2025. However, while solar activities actually ramped up faster and stronger than those early predictions, the forecasts get updated, and more recent ones suggest the peak might be happening sooner, maybe even already started, and could be stronger than first thought. Solar science is always evolving.
So more activity expected in the near term. Does that mean more risk?
Statistically, yes. The frequency of flares and CMEs increases around solar maximum. But it's important to remember that major storms can happen at any time in the cycle. We had strong storms during the declining phase of the last cycle. Preparedness needs to be constant.
Not just something we think about at solar max.
Exactly. NOAA tracks the average frequency G5 storms happen maybe 4 times per cycle on average, S5 radiation storms less than once per cycle. But averages hide variability. We need to be ready regardless of where we are in the cycle.
And because we rely so much more on technology now, satellites, grids, communications, even a moderate storm could cause more trouble than it might have 30 or 40 years ago.
That's the key point. Our technological footprint has expanded enormously, especially into space with things like Starlink. This increases our overall vulnerability. Even a moderate storm by historical standards could have significant consequences today.
So continuous investment in understanding the sun, predicting its behavior, hardening our systems, it's not optional anymore, really.
It seems crucial for maintaining the stability and functioning of modern society.
Okay, so wrapping this up. Solar storms. Definitely real, definitely powerful, diverse impacts on Earth's technology. That Iberian blackout. Probably not caused by one, based on what we know now, but understanding and preparing for space weather is absolutely vital, maybe more than ever.
A very good summary. Ongoing research, international teamwork, making our infrastructure tougher, and keeping the public informed, those are the keys to managing this natural hazard.
Which leaves us with a final thought, maybe. We keep building these amazing, complex, interconnected systems reaching further into space. How do we make sure we're building resilience alongside that progress? How do we balance innovation with the need to protect ourselves from our occasionally grumpy star? And ethically, how do we manage a risk that truly affects the entire planet?
That's the multi-trillion-dollar question, isn't it? Something to definitely keep thinking about.